is p squared, and therefore Lorentz transformations act on this 2 by 2 matrix just by conjugation, just by multiplying by 2 by 2 matrices on the left and the right. So the complexified Lorentz group, general complexified Lorentz group, is SL2 cross SL2 acting on this 2 by 2 matrix on two sides. Okay? So P goes to something on the left, P something on the right. Okay? And so you see, if these are SL2, the determinant of P is left invariant under this, and therefore P squared is left invariant, and so you've acted with a Lorentz transformation on P. Now, if the particle is massless, P squared equals 0. Okay? So for massless particles, we know more. We know that this 2 by 2 matrix has 0 determinant, so it has rank 1. And because it has rank 1, if I call explicitly the matrix with two indices, so alpha runs from 1 to 2, alpha dot runs over 1 dot to 2 dot, then this matrix is just the outer product of two two-dimensional vectors. Okay, so for instance, if I had a particle moving in the z direction, this would be the 2 by 2 matrix, and lambda would be the square root of 2e0, for example, and lambda tilde would be the square root of 2e0. And in fact, you might complain that these lambda and lambda tilde are not uniquely defined because I can multiply them by opposite, I can rescale them oppositely, and that in fact precisely reflects the action of rotations on particle moving in a given direction. Right? So if I do a Lorentz transformation that leaves the momentum invariant, I have to pick up a phase corresponding to the angular momentum of the particle. And that's exactly what this remaining degree of freedom does. So that means that scattering amplitudes are naturally functions of these variables, these two-dimensional vectors, lambda and lambda tilde. Instead of associating a form momentum with each particle, but which is constrained, I just associate two two-dimensional vectors with every external particle. Very nice, right? And it's two two-dimensional vectors, but because of this rescaling that I'm allowed to do between them, I have essentially 3 degrees of freedom associated with every vector, which is correct. Right? The 3 spatial momenta that tell you. Now, the only invariance that I can use, because the symmetry is SL2 cross SL2, all I can do is take two variables, lambda 1, lambda 2, and this bracket is just defined to be the determinant of the little matrix lambda 1, lambda 2. And similarly, you can have the other kind of bracket, which is defined to be the determinant of the matrix lambda tilde 1 and lambda tilde 2. And that's it. Those are all the invariants you will ever seek. Okay? So these brackets, so now I've expressed everything in terms of the lambdas and the lambda tildes for the external particles. And all those formulas that I wrote are now, that's it. So when I said before, the variables are roughly square roots of the momenta, you see what I mean more precisely. All right? Okay, but what I want to say is that notice these 3 particle amplitudes are incredibly simple. So that's not where the complexity is. Okay? These are very simple. But there's 2 different kinds. This is very important. If 2 of the gluons have negative velocity and one has positive velocity, this is the formula. And, oh, shoot. I always forget to fix this. This should be reversed. 2 pluses and 1 minus. You change these to the angle brackets. And why are they different? Because you'll notice that if I rescale label 1, there's 3 ones upstairs and 1 downstairs, so this picks up the factor of the rescaling squared, which is what tells me it has helicity minus 1. Okay? So 1 and 2 have helicity minus 1, you just read it from the homogeneity of this formula. 3 has opposite helicity. Okay? So if you want the other one, you have to switch from angle to square. Okay? So is that clear? There are 2 kinds of amplitude, minus minus plus and plus plus minus. A black vertex and a white vertex, and these things are simple. Very good. So why are amplitudes complicated? The amplitudes are complicated because we don't talk, when we go to higher points, while the particles that come in and out are real and they propagate to infinity, we imagine when we draw all this stuff inside, the particles that are moving around inside are not real. They're so not real that we even give them a name in quantum field theory. We call them virtual particles. Okay? There are these virtual particles moving around, but no experimentalist sees a virtual particle. It doesn't go click in anyone's detector. It doesn't travel over infinite distances. Okay? It's a fiction. that's needed to manifest the usual rules of space-time and quantum mechanics. Okay? And this is directly the origin of all the horrible complexity. And there are even in simple scalar theories, and it gets more and more complicated when you go to gluons, you go to gravitons, it's horrendously complicated. And there's gauge redundancies and diffeomorphism redundancies and all that stuff. So the physical idea is that since that's what's directly responsible for the problems, let's get rid of them. Let's just never talk about virtual particles. Okay? So that's the beginning, or one physical idea. So what can you do if you're not going to talk about virtual particles? Well, you start to play. See, what we do have are these basic vertices. We have these basic 3-particle amplitudes. They're simple. So why don't we glue those basic 3-particle amplitudes together and see what we get? Just relax for a little while and just see what we get. So for instance, in the top picture, what I've done is put together all those different 3-particle amplitudes corresponding to the different helicity configurations. And this looks like a Feynman diagram, but it isn't, because every particle on the inside is real. Every particle is on shell. It's not virtual. Okay? So the first exercise you can do is just compute the function you get. Okay, who cares? Let's just see what you get. And first remarkable thing, if you do, let's say, 5 points, that one diagram, the answer you get from that one diagram turns out to be the final answer. Okay? That one diagram is the full answer of those 100 pages of algebra is just given by that diagram. So you get rid of virtual particles. You represent it by building things out of simple building blocks. That's the whole beauty, naively, of the Feynman's picture, right? Is that you don't have to talk about intrinsically complicated interactions. You build up in terms of simple building blocks, but by eliminating virtual particles, you make it even simpler. Now, let's say you go to 6 points. You start drawing pictures like that. Let's say you stop there. You stop there, you discover that's not the answer. When you play a little bit, you discover that if you take that picture and rotate the indices 2 over, so just add 2 cousins where you simply rotate the indices 2 over, the sum of those 3 terms is the answer. Okay? Now, you can get this by playing, but in fact, you can derive these things. There's ways with some clever tricks and some inspiration and some magic that has to happen for it to work. There are ways of actually deriving recursion relations to calculate the simplest tree amplitudes. So this is one of the revolutions that happened in the subject around back in 2003 to 2005 through works beginning with works of Witten and culminating in a remarkable paper by Brito, Cacciazzo, Feng, and Witten. Brito, Cacciazzo, and Feng first, and then very clarified with Witten. And these recursion relations allow people to just get the answer. And they have this incredibly simple form, and you could get these few-term expressions. And gradually it was realized that that's what these pieces were in these recursion relations. You can think of them as these physical-only, what we call on-shell diagrams. Okay? Because everything in here is on-shell and physical. Okay? So here's a very interesting clue. On the one hand, these on-shell diagrams are incredibly simple. The answer is very simply expressed in terms of them. But, remarkably, here it's the whole answer. But here, piece by piece, that term, for example, cannot be interpreted as a local process that takes place in space-time. Neither one of the terms can independently be interpreted in that way. Okay? Only the sum of all of them has that interpretation. And it's, for example, I told you that for something to be correct, it has to have poles in the right place. It has to factorize correctly on those poles. Well, that just fails for this. Every piece has spurious poles, but the spurious poles, by remarkable rational function identities, cancel in the whole sum. All right, so that's one feature. Another mysterious feature, though, is that unlike Feynman diagrams, where there's one set, you're just supposed to draw all of them. Here, there turns out to be a huge array of different ways of running these recursion relations and expressing the answer in this form. So it doesn't want to come out in some unique form. But you can write it this way, you can write it that way. There's lots and lots of different ways of expressing it this way. So now you see our problem starts becoming a little more concrete. Could it be, is there some way of figuring out, is there some principle that tells us which one of these pictures to glue together, or how to glue them together to get the right answer, absent simply the desire to get the right answer, right? Is there a new world that these objects come from, and does that world tell you a reason they have to be grouped together in a particular way? Now we're asking much more concrete questions. All right. And so all of this, purely from the physics point of view, led for many years to a kind of vague picture that we should be able to think of the amplitude as kind of the volume of some region in some space. And that we are triangulating this into pieces in many different ways, and all the different ways of triangulating the pieces correspond to the different ways of solving these recursion relations. And that hopefully, maybe if we did this, it would also tell us something about where all these mysterious symmetries came from. And that's what happened eventually with this story of the amplitude after around 5 years. So first of all, the energies and the momenta of the particles, the 4 degrees of freedom, you can group them into these lambdas and lambda tildes. There's slightly more convenient and beautiful variables that are just flat out 4-dimensional vectors. Okay, so the external data for every particle is just given by a 4-dimensional vector up to rescaling. These are things that live in P3. Done. Okay, you just have endpoints in P3. Okay? There's an SL4 symmetry that acts on these 4-dimensional vectors that contains the SL2 cross SL2 symmetry of Lorentz transformations, and in fact it generalizes them to the conformal symmetry. All right? So that's the data. I give you n 4-dimensional vectors. That's it, with an SL4 symmetry acting on them. But it turns out that this specifies, given that data, in an associated Grassmannian space, GK, K plus, physics wants m equals 4. In general, you can group these into, in general, you can talk about an m-dimensional vector, and all the information about the helicities of the particles is grouped into k extra components of these vectors. Okay, so if you have k of the particles have negative helicity, and the rest have positive helicity, then or in fact it's k plus 2 have negative helicity, the rest have positive helicity. You have a m plus k dimensional vector. That specifies all the external data, and that they're associated with that is an object that lives in the space of k planes in k plus m dimensions. So this data fixes some shape that lives in gk plus m. That shape is called the amplituhedron. It's a generalization of polytopes into the Grassmannian. And now, the canonical form, in the sense that I told you about, for the amplituhedron is the amplitude. Okay, just on the nose is the amplitude, and the different ways of triangulating and breaking up the amplitude in pieces give you all these different formulas for the recursion relations. There's no mention of quantum mechanics or space-time to begin with. There's all this structure in Grassmannians, and you'll see positivity and other things. But the rules that the amplitude has to satisfy, the way it factorizes on the boundaries, is all reflected in the geometry. As you go to the geometry of this amplituhedron, you discover on the boundary it factorizes into lower amplituhedra. Okay? And in precisely the way that it needs to in order to account for the physics. Okay, so let me just give a kind of a lightning picture for what some of the mathematical ideas are that are associated with it, and I'll end. I'm sorry for testing your patience. So the mathematical ideas actually go back to something incredibly basic. If you wanted to describe to a mathematical friend scattering processes, you might start by talking about particles and the momenta. Maybe that's too complicated, the momenta and the energies. So what could you do to simplify it as much as possible? You would just keep track of the particle labels. We'll give you some labels in and some labels out. So the simplest mathematical scattering is a permutation. Okay? And so this really looks dumb, right? So it's a 1, 2, 3, 4, 5 in, 3, 5, 2, 1, 4 out. But already this we've known for 40, maybe more years, that even this silly thing is actually somewhat deeply associated with particle scattering in integrable systems. And one way of seeing how permutation is associated with particle scattering is to represent it graphically. Still, I'm not doing physics. I'm just drawing lines, right? I'm now representing the permutation 1 went to 4, 3 goes to 1, 2 goes to 3, and so on. Right? But now this looks like a scattering process. It looks like a scattering process in one dimension of space and one dimension of time. Okay? Time runs up, and this is space where the particles just bounce off each other. Okay? Breaking up the permutation into a product of adjacent transpositions is not unique, and any way of doing it corresponds to a picture like this. Demanding that the answer only cares about the permutation and nothing else forces the little 2 by 2 scattering amplitudes at each one of these corners to satisfy a rule that if you move this line from this side to that side, you get the same answer, and that's the Yang-Baxter relation. Okay, so that's why these are related to integrable systems. But there we have this. A very early example of this general chain of connections. You begin with a combinatorial idea, in this case just a permutation. Then it lifts up to something associated with scattering process. Something quite beautiful about it. But people have said for years that this has nothing to do with the real world. This is one of zillions of things that's only true about special systems in 1 plus 1 dimensions. And why? Well, two obvious reasons. There's no particle creation or destruction. First, it's in 1 plus 1 dimensions. Secondly, qualitatively, there's no particle creation or destruction. And that's associated with the fact that the fundamental interaction is 2 to 2, where the fundamental interaction that we talked about is 2 goes to 1. But it turns out, from many points of view, mathematicians in the 2000s have found another way of representing permutations to be interesting. Not as obviously just taking a bunch of indices in and sending a bunch of indices out, but instead putting more symmetrically all the indices on the boundary of a disk and drawing a black vertex on the inside and a white vertex on the inside. For example, to read off a permutation from a picture like this, you walk into the graph. To know where like 1 goes, you walk into the graph. If you hit a black vertex, you make a right turn. If you hit a white vertex, you make a left turn. Okay? So if you do that, clearly if I draw a picture like this, it gives you a permutation as well. But now these pictures, just as pictures, start looking a little bit more like scattering processes, right? Real scattering processes. That's a little cool. Now, it's a nice fact that, in fact, every permutation can be represented like this, just like every permutation is represented the other way. It's slightly more detail, because there are black and white vertices here. These are actually so-called affine permutations, which means that they also keep track, the number of black and white vertices in the picture, keep track of the number of times you jump back. You have a cyclic ordering now for the external particles. So it's all permutations where you jump back k times. So 1 goes to 3, 2 goes to 4, but maybe 4 goes back, 7 goes back to 6. Okay, so if 7 goes back to 6, that would count as a k equals 1. For every jump back, you get something. Okay, so every affine permutation where you also keep track of the number of times that jump back is associated with a picture like this with black and white vertices on the inside. You can make the picture by part-time. Okay, so you have so in the math literature, so we call these things. Now notice, I shouldn't have to emphasize, they're the identical pictures. Okay, so I had gluon scattering, black-white pictures, all this stuff, and now there's something else purely from the point of view of these permutations. All right, so now it turns out that in fact they're deeply related to each other, and one of the most important things you discover when you play with these diagrams in physics is that there are certain identities that you get exactly the same answer for any one of these on-shell processes. When you glue these things together, inside, if everywhere you see a square like this, you're allowed to reverse the colors. Okay, so this is a somewhat non-trivial and important identity for these on-shell functions. Somewhat more trivially, if you have two black things, you can merge and expand them any way you like. Okay? So these are equivalences that leave the physics invariant. Remarkably, those are exactly the equivalences that leave the permutation invariant. Okay? So if you change the white to black to white for the square, any permutation you get just does zigzags right, left around it differently, but it leaves the permutation invariant. So this is a more interesting connection, right? There is a set of objects with the same pictures, and they're classified by these combinatorial objects, these simple affine permutations. All right, so that's the very bottom level. Now there's something geometric associated with it. The geometric thing associated with it is a generalization of, begins with the notion of a positive Grassmannian. And the positive Grassmannian is the Grassmannian generalization of the inside of the simplex. Okay, so we're eventually going to talk about the generalization of polytopes into Grassmannians. Those are amplitudohedra. But the first step is to generalize the simplex into the Grassmannian. Okay? So how do you generalize a simplex into the Grassmannian? Well, first think about the points on the inside of the triangle. Of course, we can think about all the points on the inside of the triangle as a weighted sum of the corners with positive coefficients projectively. So really, I can, in this C space, in the space of these coefficients, up to overall rescaling, I'm just talking about lines passing through the origin. So in P1, in the space of lines passing through the origin, there's a positive part where the C's are positive. Okay, so that's the notion of the inside of a simplex. We translated it into some positive part of the space of lines in one dimension. Now you simply try to extend this idea to the space of K-planes in n dimensions. How do I extend this idea to the space of K-planes? Well, so the space of K-planes in n dimensions is the Grassmannian. Now, to give me a point to give me some such configuration, let's say I have a 2x5, a 2x4 matrix, 2 planes in 4 dimensions. I have to give you 2 4-dimensional vectors whose span gives me the plane. So here's one of them. Here's the other one. Anything I do with these vectors has to be invariant under 2x2 linear transformations that leave the plane invariant. So I have to deal with SL2 invariance. And so what can I now mean by the positive part? Now I have 2 by n or k by n matrices. What can I mean by the positive part of this space? And I can't just say all the entries are positive because that's not invariant under k by k transformations, linear transformations. All I can say is that all the minors are positive. All the determinants, every possible k by k determinant is positive. So that's the only reasonable extension of the notion of a simplex into the Grassmannian that we could talk about. Now there has to be something else though, because unlike this case, here the minors are antisymmetric. So for this statement to be meaningful, I have to order. I have to give an ordering. Right? And this is absolutely crucial, mathematically and physically. This is absolutely crucial. Remember we kept saying this is a very arid, boring space, space of momenta. And here, I mean, you guys love Grassmannian, but to me, Grassmannian is, well, who cares? The space of K-planes, big whoop, boring, what's going on? There has to be a frisson of something, and the frisson of something is this word cyclic ordering. Okay? You say the word cyclic ordering, and all of a sudden something begins to happen. Okay? So given a cyclic ordering, you can now talk about the notion of positivity. Okay? And isn't it interesting that the cyclic ordering is exactly what we also had in these pictures and in the physics. All right? So the positive Grassmannian is the generalization of the simplex into the Grassmannian. And now there's a very natural mathematical question. How do you build matrices that have all positive minors? That sounds like a hard project. For me, it sounds like a hard problem. You sit down, you write them all, you write all these inequalities, it looks like a nightmare. But this problem was solved. It's in some abstract sense, it's part of Lustig's theory of canonical bases. I don't know what those words mean. But in a very practical sense, it was solved by Postnikov a little over 10 years ago. And it's solved in the following remarkable way. The idea is not to build, to impose the conditions flat out on the big matrix. The idea is to build the matrix gradually. Take simple matrices that are positive and glue them together with rules that keep it positive. So you begin with 1 by 3 and 2 by 3 matrices that have all positive coefficients, and then you represent them by exactly these black and white pictures. And then there's a canonical way of gluing them together and reading off a larger matrix from one of these guys, which hands you a matrix that looks like this. Not a random matrix, but in terms of the basic positive variables of the pieces, something that looks like that. So you notice the sort of cunning appearances of B, B plus B, B plus B plus F, and so on, that guarantees that when you take any minor here, it's manifestly positive when all of the entries are positive. And here it's pretty simple, but when you get to higher K and so on, it's really, if you didn't know where it came from, it looks very magical how it works. But of course, that's the idea. You're building it up as these elementary building blocks, gluing them together big positive matrices. So again, now purely from the point of view of total positivity, A, we have the combinatorics, that's associated with scattering pictures. B, now we've uplifted this. We're trying to build totally positive matrices, and to do that, we're gluing together black and white vertices in a way that looks exactly like the particle scattering process. So, what's the connection? So finally, there is a connection, of course. Okay? And the connection is that every one of these on-shell diagram pictures is associated with a cell of the positive Riemannian. So the positive Riemannian, there's a region where all the minors are positive. Then you can go to boundaries where some of the minors are set to 0. Because the minors satisfy relations, Kluger relations, the boundary structure of the positive Riemannian is extremely rich. Okay? It's not like a simplex, whose boundaries are just simplices. So it's a very rich structure. And the boundaries, all the boundaries of the positive Riemannian are associated with these black and white pictures of the right sort. And in fact, when you give me the energies in the moment of the particle that specify this 4x(n) matrix, that 4x(n) matrix selects by the property of being orthogonal to this k-plane that we're talking about. So this 4x(n) matrix is itself a 4-plane in n dimensions. It's naturally orthogonal to some k-plane in n dimensions, and that picks out a cell of dimensionality 4k. So you give me any cell of the correct dimensionality, and that cell, by the requirement of being orthogonal to the 4-point associated with z, completely fixes where you are in the positive Riemannian. And then, if you take each one of these pictures, is also associated with a canonical form, where you take the d log of all the positive coordinates associated with the little vertices. Okay? You take that differential form on the support, and it precisely computes that on-shell diagram. Okay? So that's a connection. So there's one more layer. Right? There's the combinatorics. There's something purely inside the Riemannian. Then you add this plane of external data from the outside that then picks out of the positive Riemannian cells of a particular dimensionality, and on that intersection, absolutely just evaluates to what the physical processes are. Okay? I hope it's clear. This is not, you don't just roll out of bed and say, oh, it's obvious that gluons are connected to the positive Riemannian. This is a surprise. Okay, this is a surprise, but it's an example of the sort of surprise, as I said, that we should be looking for if the kind of ideology that I was talking about is correct. So, all right, so that story was just about the building blocks. Remember I told you that the amplitude could be computed using recursion relations, blah, 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 with building blocks in various ways. And so each building block is associated with cells of the positive Riemannian. And that's where the story was as of around 5 years ago. But then we had one more problem. Why are we taking those building blocks together and gluing them in a particular way to get the full answer? So we still don't know the answer to that question. And that needed an extension. So the positive Riemannian, to our great luck, had been understood almost around the same time as we needed it by Alex and friends and other people. But what the further development of physics needed was an extension of these ideas to something new. So, roughly speaking, the triangle generalizes to the Riemannian as a positive Riemannian. That's one generalization. There's another generalization to a polygon and to polytopes. And the cousin, the way the inside of a polygon generalizes into the Riemannian is the amplitahedron. The amplitahedron is the analog for polytopes of the positive Riemannian for simplices. And there's one thing I will have no time to talk about, but this is what gives you tree processes. There's a canonical way of sort of hiding and ignoring particles that actually calculates the full loop amplitudes in the theory and takes you from trees to loops. But I won't really won't have time to talk about any of it, but I just want to give the quickest intuition for what this generalization is. So let's go back to polygons. So I want to talk about a convex polygon, and I want to talk about all the points on the inside of a convex polygon. Then first, for the polygon to be convex, if I want to describe the external data as projectively using three-dimensional vectors, then I would say that every minor, every determinant that I make with 3 consecutive z's has got to be positive. That just says they're all oriented in the same way. So first, just the correct shape of the external data demands some positivity on the external data. Okay? That's one thing. Second, to be inside, I have to be in the convex hull. Okay, so I have to take a positive combination of this positive external data. So you see, even something as basic as the inside of a polygon is a slightly interesting jamming together of 2 positive things. Positive external data in G plus 3n here, as well as positive coefficients here that in this case are just in G1n. All right, so that's the inside of a polygon. So how do we generalize that into the Grassmannian?